All right, fine. I think we can start. First of all, I'm really excited to be here in HTML5 Developer Conference because I believe that HTML5 is a path to the future. And mobile, be it mobile web or native mobile applications or hybrid mobile apps, is the future indeed. And you know what? In the future, there are no network of websites. In contrast, there are network of things, as they say, or there are a network of applications. That's what makes mobile so important for us. But before that, let's rewind back to present time and go with a case study. So picture this. You are the next person in line to buy some snacks, and your movie is just about to start soon. What will you do next? Chances are that you'll pick up your phone and check in from Foursquare, or, I don't know, poke someone on Facebook, or maybe check your junk emails and archive them. The thing is, there is some hidden anxiety in this situation because your time is limited because you don't know when the cashier will call you next. And that limited time and attention and the anxiety is exactly the reason why developing responsive, simple, and intuitive mobile applications is a thing that we have to pay attention to. And in this talk, we'll learn why creating mobile JavaScript applications is a pain in the ass, and what we can do to overcome the challenges and limitations of mobile. And before that, let me briefly introduce myself. My name is Volkan, and I'm a mobile engineer at Jive Software. And Jive is a platform that makes work more productive, I can say. Or Jive is a place that makes Monday mornings suck less, basically. And the slides and resources of this presentation, along with the source code and along with my former presentations, can be found at volkan.io if you want to. There are links to other stuffs. Basically, they are slide speaker deck links just as a pointer to resources. And in this talk, basically, in a nutshell, we'll try to figure out whether it's really possible to create a really fast JavaScript mobile application in a runtime context, which is really constrained in a place that we don't have too much freedom in terms of RAM, CPU, and other stuff, and in a runtime environment that is somewhat familiar but not so familiar to us. So JavaScript is a really nice language if you love to use JavaScript, but for other people that come from more object-oriented backgrounds, it's kind of a pain in the rear, kind of, and we'll try to figure out those kind of stuff. And first of all, there are a bunch of limitations and challenges of mobile. You may wonder what they are, and they are can be separated to different categories. One of them is network, the other is the battery, the other is memory, and the other is the overall processing power. In mobile, network is really flaky. It's not well behaved. There is high latency in network. Things go offline and online all the time. So you have to learn to live with latency. And the other thing is, typical mobile devices don't have gigabytes of RAM, maybe 1 gig, but it's also shared with a bunch of other applications. And therefore, you can assume that it has a half a gigabyte of RAM, so it's not abundant in terms of memory utilization. And also, mobile processors are optimized for different things. They are not optimized for fast computations. In contrast, they are optimized for low current consumption and low heat dissipation so that it doesn't eat up your battery quickly. Therefore, which makes us conclude that mobile processors are also slow. And when we keep in mind all these constraints and limitations, we can come up to another thing is also battery. And battery is really important in mobile because battery is limited, and your users would not like an application that drains battery too quickly. If the application drains battery, I have seen instances on Twitter that people are literally swearing at the companies which their applications are taking the battery in from 100% to 30% in half an hour or so. So you would not want your users to be like that, you know. And battery has a bunch of things that consume battery a lot. One of them is the network requests. Actually, the network request is the second most a resource-consuming thing. The first thing is the LCD screen. The shiny, bright screen consumes a lot of resources. And the second thing is the radio, because the network request is basically a radio communication from the device to the base tower, and that consumes a lot of energy to maintain that relationship, basically. And the second thing is JavaScript, because JavaScript means computation, and the more computation you do, the more processing you make, the more the battery will be eaten up. And the more layered an architecture you have, the more object-oriented code you do, the more the memory is consumed, basically. And another aspect is images. The rule of thumb is to use as little images as possible in your application and not to render the images that are outside the user's current viewport. So another thing about images is never ever try to scale them, because it makes the application real slow, and it also consumes a high chunk of battery. So it's kind of a two shoots at one arsenal, kind of. So it's really double bad. And the other thing is DOM. As a rule of thumb, you have to keep the node depth and node breadth of the DOM limited. So if you have more than 5,000 nodes in your application, or if you have more than 12 to 15 levels of DOM nesting, then your application may suffer from the consequences. And having said that, we can come up to a conclusion that mobile and desktop are two different worlds. They are both designed to navigate stuff, basically, in a very basic sense, but desktop is more powerful and mobile is more flexible, kind of. And if we embrace the fact that mobile is something more general purpose and more lightweight, then we can create really excellent applications for mobile. But otherwise, if we try to treat mobile as desktop, then we will really suffer from the consequences. I don't know whether you watched the Christian Heilmann's keynote talk, but he was saying exactly the same thing. If you try to make an application as fast as native, then that's not the correct way to go. The correct way to go is to embrace the facts and boundaries of the mobile and create a mobile application, not something that's real fast and awesome, kind of. But speed is, contrary to that, is also important in mobile, because the users' expectations are limitless, and our users want us to be fast, and they want us to be even faster than desktop, because as we have seen from the movie analogy before, the expectation of the user and the time and the attention of the user is limited. And also the user's precision is limited. The thumb is fat, you know, and therefore you have to make it really tiny, intuitive, responsive, and to the point kind of an application to make it work for mobile. And when it comes to speed, speed has 5 major dimensions in mobile. One of them is the network layer. The other is the overall rendering performance. The other is the cache layer. The other is the reaction, which is the overall user responsiveness. And the other is the JavaScript execution speed. And I can assure you there are literally books written in each and every single item that you see here. So I won't be diving into too much detail. I will be just giving some broad brushstroke overview of those items, so that if you want to drill down further, you can go and research on your own. So the first thing is the funnest one. Let's start with the network layer. These tests were taken on my home, and when I was doing those measurements, my phone was a mobile phone was stationary on my desk. And as you see, these results are not so, so optimistic. And things might have been really, really worse if I was actually indeed mobile, like, driving at 70 miles per hour on US 101, or on the train going from some destination to another, and my mobile device was doing handovers from one base station to the other base station, then probably I would have seen something like this. The thing is, I don't know you guys, but many of my applications that I use on my device falls back to this infinitely twirling spinner state when I'm on the train. And that's exactly the way that the users do not handle the offline, or the creators of the application not handling the offline state as elegantly as possible. So mobile has high latency, and you can expect latency numbers starting from half a second for each of every single network request you make, up to, depending on the state of the network and state of the base tower, up to 3 to 4 seconds of network delay. And therefore, you have to learn to live in a lossy network condition. And to deal with latency, there are a bunch of tips that we can depend on. And one of them is to reduce the number of HTTP requests. Since sending a network request is really expensive in terms of speed, and I see Ilya is out there, and he knows better than me, I guess, on that topic. And I strongly suggest to go and read his new book on browser network architecture. It's really much in depth, and I don't have too much time to dive into those kind of details. So the latency is really high, and you can batch those network requests and kind of combine them and send them in batches. Because mobile networks are not optimized to send small bits and pieces of data. Instead, they are optimized to batch a request and send big chunks of data. So buffering a request and sending and receiving them in batches is really helpful. The other helpful thing in buffering a request is useful when it comes when the network goes offline. When the network goes offline, you can buffer your requests in a collection of some sort, and then when the network goes back online, you can replay back them together. And the other thing is to decouple the user experience from network activities. Since we cannot rely on the network connectivity or the quality of the network, we should use optimistic actions. So if the user presses a like button, we should render the UI as if the user has liked it and send the request and process it in the background. Or if the user sends a message, we should update the UI as if the user has sent the message, and then do our calculations in the background without the user realizing it. That was a network thing. And one other thing about network communication is to abstract away your data access layer. Because since the mobile network is really hostile and really variable, you have to do some kind of optimization, and you would not want those data access optimizations to be spread around all your code base. So if you kind of make a JSON API request in this manner in your code, then it's not a good practice. Instead, you might want to do something like this, like abstracting the data accessor method to its own data layer, and do your kind of defensing against the network conditions in the data layer yourself. And the other thing is abstracting your rendering layer is also a good practice, because when you abstract your render layer into methods, it will be easier to profile them. Or if there is some kind of a jankiness in your application's behavior, or if there is some render bottleneck, then you can easily spot it out and debug it if the render layer is also abstracted in its own, basically. And as we said, latency is a killer, and generally it's the latency that's the problem. And the bandwidth, the overall bandwidth allocation is more than enough for a mobile device to communicate to the origin, basically. Since in a typical mobile application, you are just sending a sample basic JSON request and getting some numbers and data. And so bandwidth is not a big deal if you're not streaming music or streaming video or something. But it's latency, and the latency is really variable, and it's really depends on a lot of stuff. And as I said, you can go to this link below and kind of dive into the details. Since it's outside the scope of this presentation, I won't go too much into how the latency works in mobile. But the fact is, latency is high, and latency is highly variable. And to defense against that highly variable latency condition, we have to have an offline mode and embrace the offline mode. And to have an offline mode, we have to cache our responses, and that begets the necessity of having a caching layer, which will come to that further along. And also, we need to have an intelligent retry strategy. One of the things that the mobile applications sometimes forget is to stop retrying the request once the network goes away. This kind of retrying to connect to the origin over and over again consumes a lot of battery and heats up the device. And this is really, counterproductive. Instead, you can have a clever backup strategy and try a request for a while, and if it fails, you can try it after 2 seconds, and if it fails, you can try it again after 4 seconds, and if it fails after a certain number of attempts, you can just give up and either return a failure or just sync the request to null without doing any kind of action. And the other thing that's related to being fast is the rendering layer. And rendering, when we think about rendering, the first thing that comes to our minds is CSS. And mobile devices are, although they are getting better because Chrome is pushing a lot of stuff into the shadow rendering performance recently, but they are not on par with the desktop browsers yet. And a bunch of CSS attributes like shadows, gradients, large fonts, and big borders kind of create really nasty render time problems. And if you combine more of these together, then your CSS paint times will be dramatically slowed down. And the other thing is to avoid animating stuff or use as little animations as possible. And the key thing is not to use JavaScript for animations, because CSS is much more optimized for animating things, and we have to always use CSS for animations and never use JavaScript for animations, basically. And the other thing about rendering is the templates. And the importance of templates is templates are in the bottommost layer of our rendering hierarchy. So anything that we use, we do to make the templates work counterproductive or slower will affect the entire render layer. And the more logic you put into the templates, the slower they will get. So the rule of thumb is to try to use as little logic as in your templates as possible. And using logicless templates has a bunch of other advantages too. Because if you, let me think, if you want to transfer your template from the client, the device, to the server, for I don't know, for a business logic change, you want to render the template on the server instead of the client, then transferring the logicless template from the client to the server is much easier than moving a template with a logic inside it. Or if you want to do the otherwise, if you take a server-side template and put it on the client, using a logicless template will prove itself to be much more versatile. And the other thing is not to nest templates and not to nest view objects, especially if you are rendering a kind of an infinitely large scrolling list of items, then nesting view objects will prove itself to be really counterintuitive and really may slow things down. From my observations, I have seen that a typical infinitely scrolling list setup can slow down up to 3 times if you use a nested view instead of using just a dummy template. We'll see an example of this shortly. But the rule of thumb is not to nest view objects if you can. And one other thing is DOM. Touching the DOM is like kind of, do you know the game of don't touch the ground is lava, don't touch it kind of? This is a picture of this depicting it. DOM is just like that. DOM is lava. DOM is kind of a hot coal that you're grasping in your hand. And you have to yield it as fast as possible so that it doesn't burn your hand. The thing is, DOM is a sync API, and the JavaScript is also a single-threaded runtime environment. So the more you touch DOM with JavaScript, the junkier your overall experience will get. And the other thing is not only writing to the DOM, but also reading from the DOM can also trigger style calculations and reflows. So touching means don't read the DOM and don't write the DOM if possible. And if you are doing a bunch of DOM operations, then either take the nodes offline and do some offline manipulation, or batch your DOM operations together so that you decrease the possibility of style recalculations and kind of layout trashes. Having said that, there are ways to detect and measure the overall rendering cost of the application. Chrome developers tools have really great devices that we can use it. So, for instance, you can enable the continuous repaint mode on a Chrome developer tool, and then you can change the bits and pieces of the user interface and the JavaScript maybe, and then kind of compare and contrast what changes overall frame rate in what direction. And if you want to drill down further, and you want to go somewhat more low-level-ish, then you can use the high-resolution timing API. In this sample benchmark, we are doing just that. We kind of create an element, and we hide the element first, and we flash all the style changes, and then we show the element, and we flash the style changes again. And in between two operations, we take 2 timestamps. And these 2 timestamps can give a rough estimate of the overall rendering cost of that chunk of DOM. And as always in these kinds of benchmarks, you have to repeat the tests over and over again 20 times or 100 times, and then kind of weed out the edge cases and average the remaining part to come with a statistically significant data. But anyways, this kind of approach is available for us, and you can use high precision timing API to come up with how long a chunk of code takes kind of measurements. This is the example related to not nesting view objects. In this sample, we see a repeater structure that is creating a child view and rendering it and populating it into a DOM fragment. I have seen worse codes than that. This is not the worst thing that you can see around, but still this has its own disadvantages. One thing is, if you can see, we are just rendering the view, and we are passing the outcome of that rendered thing to a fragment, and we are not using the view object afterwards. Therefore, the shiny new created view object is just marked for garbage collection at that case. And if this happens in a really active hot code path, like an infinite scrolling list of items, then we are kind of bombarding the garbage collector with view objects to be destroyed. And it will not make our garbage collector happy, and it will slow down our overall rendering performance. And we can do something simpler than that. Instead of using a view object, we can just use a precompiled template instead. And instead of rendering each item as a view, we can pass the data to a template function. And that template function can create a partial HTML, and we can join the HTML buffer and come up with a faster rendering solution. This really proves itself to be useful if you are, as I said, if you are scrolling a large list of items. And there are a bunch of tips and tricks on rendering infinite scrolling lists, and it's really a pain. So if you dive into that path, I don't know, good luck with you. And the other thing is we can do even better than that. If we know, assume that we have a big list item and we want to refresh it, but we know that parts of those list items change and the other parts are not changing, they are remaining as it is. And if we kind of know which parts of the application has changed, we can create a delta of those changes, and then for each item we can incrementally update the view instead of rendering everything from scratch. This is a useful approach, but the thing is, if you are following up, the more kind of optimizations we do in the code, the harder it gets to manage and the harder it gets to tackle with. So before doing those kinds of optimizations, just measure your code and check and verify whether it's really worth doing that optimization. As always, don't fall in the trap of premature optimization, because optimization without measurement is kind of an effort in vain, basically. And the other thing is Jank Busting. And there is a related talk after this one. I strongly suggest you to go and visit that if you are into creating jank-free user experiences, basically. And also, there is a site called jankfree.org. If you haven't heard of it, I strongly also suggest you to go there and watch the videos and read the articles. It's really quality content there. And I won't dive into too much detail because my time is limited. The thing is, you have 16 milliseconds per frame, roughly. And you need to maintain not only that 16 millisecond frame rate, but also you have to be consistent in your frame rate. And to be consistent in your frame rate allocation, you have to utilize the request animation frame API. We'll see a bunch of examples regarding the request animation frame further along as well. And the other thing is GPU acceleration. And luckily enough, another talk is being done after my talk. So I won't go dive into the details of this as well. Go and watch it. The thing is, the transform translate Z hack works really nice in a desktop browser with a lot of GPU RAM. But the mobile device has a really limited amount of VRAM. And since the video RAM is limited, it's really, you have to be really picky to select what part of the components you need to translate to GPU acceleration. And the other thing about mobile devices is on some of the mobile user agents, transferring the bitmaps from the CPU to the GPU takes more time than usual. So if you kind of exhaust the GPU utilization and kind of exhaust the video RAM, and you'll come into a scenario like, the video RAM is exhausted and you are trying to transfer bytes from the CPU to the GPU and backwards, and there is not enough buffer, and 9 out of the 10 times this will cause an application crash. So I'm not saying don't use GPU acceleration, just know your application and test it wisely before diving into that path, basically. And the other thing is maintaining the 16 frames per second is refresh rate. And as we can come to a conclusion, 16 frames per second is not only for games. It should be maintained in every single action, like swiping, pinching, zooming, sliding, or in the screen changes. I just want to poll the audience here. You see the animation illustration there. How many of you guys have had an application like an infinite scrolling list, and you scroll, and it starts like getting jankier and slower, and then you kind of, hate yourself because the application is not manageable at all. The thing is, creating an infinite scroll experience is really hard, and there are really different kind of optimizations that you have to dive into to create that kind of an experience. And therefore, if you don't have to, don't dive into that path, because some of the frameworks claim that they can come up with as fast as native infinite scrolling performance, and I have been trying to come up with a solution for the last 2 years, and I haven't come up to that as fast as native solution. And I can say that it is technically impossible to come up with that kind of a solution, because you are running that application on top of your native rendering layer or on top of your operating system. But you can come close if you do optimizations enough. And to do a bunch of tips for that is, one, you can limit the size of DOM and limit the size of the things that you scroll. And the other thing is you can kind of try to make the height of the containers fixed. So if you are scrolling a fixed height set of items, then it will be much easier to calculate what to put in where, kind of. But it's still a pain. And the other thing is the caching optimization. As we have seen, we have a problem because our network requests are unreliable and expensive in terms of response time and delay. And one solution is to batch your requests, as we've seen, and then cache your responses. But that kind of solution opens yet another can of worms. That question is where you can cache. There are a bunch of options like IndexedDB, HTML5 application cache, and stuff. And it turns out that if you can live with a simple solution, then that thing works better. And local storage is the simplest solution that you can rely on. Local storage is a really fast key value store, and it's really standardized, it's really optimum. And if you can live with it, don't try to dive into other technologies. Of course, your application and your requirements might be different than the typical case, but I'd suggest you to try to live with local storage if you can. But that doesn't solve the entirety of the problems as well, because when you find where to cache, you also have to find out how to cache stuff, which comes out for us to devise a caching procedure or caching algorithm, so to speak. And one challenge is our cache size is limited if you are using local storage. Although 5 megabytes should seem like a lot, in practical real-life applications, you can see that you will be exhausting that 5 megabyte limits in no time. To solve it, you can store partial data, like get the initial header or initial description of an article, and then retrieve the rest of the article from your REST API server. Or you can decrease the JSON payload. So instead of if you want a banana from the JSON, for instance, instead of sending a gorilla that holds the banana and the entire jungle with it, you can just send a small chunk of the response and cache it wisely. And one other thing that you can do is to compress your data. There are libraries that can do that, but compression also comes with a decompression overhead. So you have to think about it, and you have to benchmark your application in your target devices to come up with a wise and a viable solution, basically. And as we have seen, abstracting our rendering layer and abstracting our data access layer was proving itself to be useful. And also abstracting our cache layer and creating a single cache entry point is also a useful approach. So have a single cache entry point and also cap the size of each of your cache entries. So if somebody tries to put a 5 megabyte blog post into a cache, then you just reject it because it will blow up your entire cache, basically. And when there is cache eviction is also something to figure out. And generally speaking, there are a bunch of algorithms that can handle this, and the last recently used algorithm is the best way to handle the cache eviction generally. And the other dimension of speed is overall user responsiveness. And when I say overall user responsiveness, I'd like to emphasize that we have to keep the user feedback above everything. So we should aim to not to block the UI. So if the user is doing something, the UI should respond accordingly. If the user is doing a gesture, the UI should move. So if the user is panning, the UI should enlarge. This is really common sense, but as we are developing our applications, we sometimes forget this. When the user is in motion, so does the UI should be. And there are two key metrics in here. One of them is the 16 milliseconds per frame limitation. We have to do every kind of JavaScript in this kind of short amount of allocated frame. And if we cannot do our stuff in 16 milliseconds, we have to yield it to defer it to a later process, or kind of yield the computations to a background worker, and try to stay to be within our budget. And the other thing is, for the action to be realized as smooth as possible, the UI elements should respond within less than 100 milliseconds. So if the user is tapping a button and nothing is happening for half a second, then that's poor user feedback, and you would not want that. The UI should be always responsive as much as it can be. And this is another thing that I experience in infinite scrolling list stuff, basically. While you are kind of end of the list and you are scrolling, sometimes the screen freezes for 1 or 2 seconds. The reason for that is the application is trying to make an AJAX request in the background and then trying to populate the user interface with the results that has come from that AJAX response. There are two things about the AJAX callback. One of them is AJAX callbacks can block the request animation frame loop, and the other thing is the AJAX callback response can block the UI thread, basically. So therefore, when an AJAX response comes, the UI freezes until you exit that callback situation. And to sort this out, we can come up with a simple solution. Like we can have a flag that indicates whether the user is interactive or not. And if the UI is in motion, we can wait for the AJAX manipulation for a while and defer our execution. And when the UI is not in motion, we can ensure that the user is stationary and do our updates accordingly. The advantage of that is, even though our UI manipulation can take a long time than usual, the user would not realize it because, I don't know, maybe she is scrolling a little and she saw an article and she stopped scrolling and she is reading the article, and then we are doing the updates and the user is not recognizing it at all. This is kind of a good practice. If you can adjust it, it will be better. And the other thing that we can speed up is event handling. And as I said, we should prioritize UI responsiveness. So if and that leads us to a approach to use optimistic actions, basically. So if the user taps a button, don't wait the AJAX request's response to come to update the button state, or just update it immediately. So if the user is sending a message, render the UI as if the message has been already sent. The other thing is event delegation. Event delegation is a technique where you attach to the container item and let the events on the child elements propagate up to the container. It has a bunch of advantages. One of them is you decrease the number of functions that you have to deal with, and it's also efficient in terms of memory and in terms of overall response time if you are using too many event handlers. So try to use event delegation as much as possible. There are a bunch of caveats to that, like some kind of touch event handlers might be better if you don't use event delegation per se, but you have to measure it to know about it. But as a general rule of thumb, event delegation is good. The other thing is frequently detaching and attaching events. If you find out that you are adding and removing events more over and over again, then one choice would be to delegate that event to a higher container, and the other is to try to find a way that doesn't use events at all, kind of. And if you follow these approaches, you'll see the effect in your application's speed and responsiveness, especially in older user agents like older Android devices, basically. And the other thing is some kinds of UI events are really nasty because they fire a lot. And the concept is you have to decouple your user interface modification or DOM manipulations from the UI handling code, basically. So in this sample code, we are kind of touching the DOM every time the device moves. And this is a counterproductive approach because the device motion event fires a lot. When you change the axis, tilt, and movement of the device, the event will fire like crazy. So instead of doing that, we can decouple our kind of algorithms, and we can create a state bag that stores the UI state whenever the event is fired. This state bag doesn't hurt us too much because we are not touching the DOM in that case. We are just updating a single state object. And we can defer our DOM update to a more proper place, to the request animation frame loop, which will be more efficient. Because in the animation frame loop, we are kind of sure that it's the perfect time to do our rendering actions because the browser ensures that for us. And this is much better in terms of responsiveness. Especially, you tend to fall into this trap when you are adding scroll handlers and similar kind of handlers. But as a general rule of thumb, whenever possible, try to decouple the UI modification from the event handling code, basically. And the other thing is to increase the speed of overall JavaScript execution. And when it comes to the JavaScript execution, it's not the JavaScript only. So optimizing your, branch tree traversal search algorithm won't take you too far. The thing is, JavaScript is in constant interaction with DOM, CSS, the browser, the rendering, the parsing. And in a typical scenario, what kind of slows things down is some kind of big chunk of the layout being trashed over and over again, or some part of the page being rendered too many times per cycle, kind of. So generally, the bottleneck is in the DOM or the rendering layer or the parsing layer. And to find out what's causing the problem, you have to know to measure it. And one other thing is the concept of entropy. As in code, as in life also, entropy in code also increases. And I can say that code expands to fill timeframes available to you. This screenshot was taken from real production code, and we were able to reduce that chunk of flame chart down to half the size by doing black magic, like deferring events to later phases, using background workers to optimize stuff, joining some of the events, and removing a bunch of redundant events. But that's not what I'd like to discuss. What I'd like to say is the code doesn't stay the same. The more you write the code, the more it expands to fill out your allocated frame budget. So you have to constantly measure, optimize, and remeasure it in a Kaizen-like cycle to make your code always in ship shape. And there is also another side of coin, because browsers are getting better as well. So Chrome is doing crazy stuff on shadow rendering and background JavaScript compilation. There is branch prediction algorithms on the devices, and also JavaScript, especially in V8 browsers, use a hidden classes concept, and also does a bunch of code path optimizations. So it can detect that the path of code is hot and optimize it accordingly by inlining some chunk of code inside it. So the bottom line is the engines are getting better as well. And there are two corollaries to that. Corollary one, as the engines are getting better, the first rule doesn't change. The code still expands to fill the time frames available. So the more computational space you have, the more code you cram into it, and the overall result doesn't change. And the second corollary is, since the engines are doing all kinds of weird optimizations in the background, you cannot know how your applications behave just by reading the code. You have to measure the application in context and benchmark it according to your platform, preferably on a real device, because emulator or simulator is not also good in benchmarking stuff. And the other thing is frameworks. I have a love and hate relationship with frameworks, and you can go back in time and listen to Chris' talk if you like. It was a really nice talk about the craziness of and the abundance of frameworks, kind of. And frameworks, especially in mobile, have economies of scale. And when I say economies of scale, I mean if you don't use the entirety of the framework, then it gives more harm than good. And generally speaking, your mobile application doesn't need the entire framework per se. And frameworks are not optimized to make things fast. They are optimized for readability, reusability, cross-browser compatibility, and therefore they are different kinds of beasts. And when you use frameworks, you are kind of married to them, and it will be hard to switch between frameworks. You have to manage patches to them, you have to manage upgrades, and if you find some kind of quirky behavior in the framework, the ideal way of doing it is to patch the framework and submit it to GitHub and wait for the merge to be forked to be merged, and then use the updated kind of framework on your code. And this is a really vicious cycle. So I'm not saying not to use frameworks, I'm not suggesting against them, but just be aware of the consequences. And to display what the impact of a framework would be, I just created a simple setup. This is nothing fancy. It's a basic underscore backbone jQuery mobile application. One thing that I did was to add a simple counter on each and every single function of those frameworks. And you can also do much deeper instrumentation using Esprima.js, but this was also good enough for the demonstration purposes. So the results are kind of stunning. So after loading all those frameworks, I have counted 6,827 function calls. And these are just to warm things up. No backbone view has been created. No jQuery mobile widget has been initialized. If you go back, this is just a simple dummy HTML page, and its cost is really kind of huge. And that's not the entirety of things. You also have to put your business logic, because you're doing some kind of business preferably, your data access layer, your cache, and you also have to add a bunch of other helper plugins. And when you combine all this, your framework becomes kind of like this. I don't know you guys, I love burritos, and frameworks are like burritos. They are delish, but they are harder to consume and harder to process. So try to remain lightweight if you can. At least you try to, weed out the unused parts of your frameworks to come up with a, lightweighter solution. And since we are dealing with mobile, we are using kind of more modern APIs, and there are a bunch of alternatives to using framework code in the standard way of doing things. It might, look some kind of typing stuff longer, but you can kind of write wrappers around it and kind of create a mini library of your needs, basically. And the other thing is memory leaks. I don't have too much time to dive into this as well, but keep in mind that memory leaks are not magic. It's basically there is some kind of a reference that you are not dereferencing, and therefore it's leaking. And memory leaks in mobile are really a pain because most of the mobile hybrid JavaScript applications are turned on for a long time. So the application can stay online for an hour, for 2 hours, or for a day maybe, and the memory leak will be added up and up and up, and it will then make your application harder to use. And you have to be testing for the leaks. And before that, there are a bunch of common causes for the leaks. One of them is and the most common one is detached DOM trees, and Chrome developer tools and heap profiles are really excellent in doing that and finding that out, basically. And the other is an event handler that is wrapped around a detached DOM tree that you are not unbinding. And the other thing is timers that are not cleared, and the other thing are the cache objects that are not being evicted. And as the time goes by, you try to convert those kind of stuff in your mind intuitively to other things. So there are some not so usual suspects. For instance, closures might be a cause of memory leak because closure is a controlled kind of memory leak. And if you have a cache object in the closure, then it will leak basically if you don't manage it. Also, the R objects like controller, renderer, manager. I hate those kind of terminology, by the way. Instead of controller, why don't you name it as controlling or something else? Or is this a manager, or somebody else, kind of? But aside from the fact, all those kind of managing objects, since they have state, they might kind of leak. And anything that touches DOM may leak because generally when you touch DOM, you try to cache the DOM node instead of caching an attribute of the DOM node, which should be the way to go, basically. And any object that acts like a cache layer can leak. And I don't know you guys, but profiling memory is really hard. And I would not want you to go to that path. You try to write code that doesn't leak in the first hand. And if you have to profile and find out memory leaks, there are a bunch of techniques. One of them is called the 3 snapshot techniques, which is you take a heap snapshot, then you do an action a couple of times, then you take another heap snapshot, and then you revert your action the equal amount of time, and then you take another snapshot, and then you compare those snapshots, which kind of gives an impression of what parts of your application is leaking. It's not quite easy to see, just pinpoint the leak, but it's helpful approach-wise. And the other thing is to reduce DOM access, because as we've seen, DOM is a synchronous API, and JavaScript is single-threaded. So consider all your DOM manipulation. Actually, consider everything that you do with JavaScript as a Node.js event loop. Try to do stuff as fast as you can, and then yield as fast as you can, because the JavaScript has a single thread, and you don't want to make that thread busy. If you have larger computations, you can utilize background workers. Or if you have something that you can delay that you don't need right now, you can delay it with a set timeout, basically. And when it comes to web workers, since we are still in the mobile realm, web workers are supported in most of the mobile browsers. And you can use them, and you can yield the computationally heavy operations to them. One problem is you should not abuse the web workers too much, because although it's a convenient thing to have, web workers also eat up battery. So nothing is free of charge in life. So you have to learn to be lean in your approaches, which segues to the fact that we have to be lean in everything that we do to make a really responsive, fast, and intuitive mobile application. And by being lean, I mean trying to do as little as possible. Try to reduce your JavaScript. Try to reduce your radio communication. Try to batch your radio network requests. And try to reduce your DOM, and try to touch DOM as little as you can. And the other thing is, the user experience is not the thing that you measure. Benchmarks are totally different concept-wise from what the user expects or what the user does. You might think that your application is real fast, but if the user doesn't feel like so, then it's nothing, basically. And to make the user perceive that the application is fast enough, there are a bunch of psychological approaches that we can take. One of them is overestimating the remaining time. So if you see a progress bar that says that the download progress will finish in half a minute basically, and it then finishes in 5 seconds, then you feel like, yeah, the application is real fast, and my download was really so fastly happened. But if it's the other way around, if you estimate 5 seconds and the download takes half a minute, then you'll see and you'll feel like the application is really slow and sluggish. So this is basic human psychology. Take advantage of it, basically. And the other thing is feedback that starts earlier fails to finish sooner. So as soon as the user taps a button, change the state of the button and put a kind of a spinner if it's going to do a long kind of application instead of waiting for a network request to come back. And when it dubbed, trying to keep things simple is a way to go, because simple code runs faster, it consumes less memory, it requires less resources, and if you can try to downscale, don't upscale your application basically. And also, everything depends on your context. So whatever you hear here don't take them for granted. They are just like guidelines that you can consider whether they fit for your application or not. And you have to benchmark, measure, and verify your application's behavior within the context of your application to make sure that those kind of things work for you as well. And there's always a trade-off. So you might do over-abstraction, but the code might be harder to maintain. You might utilize some kind of caching algorithm, but there might be some other side effects. And each application has different performance needs, and each application has different performance bottlenecks. And you'll never know what those kind of bottlenecks are without measuring it. And as each application is a different beast of itself, you have to always measure things and never assume things, and always be testing your application. For the people who are using the agile methodology or Scrum, and if you are doing daily stand-ups, make this performance discussion as a part of your daily stand-up, basically. Discuss the overall performance of your application each and every single day, and make it a feature of your overall work cycle. And the other thing is, this is a really nice advice. You should use tools, not the suggestions or not the rules, because performance advice is changeable. Everything changes. Whatever I say here will change after a year. Actually, I have given a similar talk a year ago, and I have weeded out a bunch of slides from the presentation because they already changed, basically. So you cannot be sure of the behavior of the application without measuring it. And also choose the tools that you'll use. And the bottom line is, know your application, be lean, and know that each added feature has a cost, and don't upscale, try to downscale as much as you can. That's the way to live in the mobile environment, basically. And in knowing your application, as I said, the simulator or emulator does not work well. So you can test your application in a desktop browser to have a vague idea of how it behaves, but keep in mind that the overall mobile performance or overall mobile behavior would be 4 to 6 times slow depending on your user agent or your device, or whether it's an application or a website kind of. And therefore, you have to test your application on a real device, on a real mobile network, because you cannot observe the latency if you have a really high-speed wireless network on your testing environment. And another thing, as I said, is entropy. Your app's performance won't stay the same, and entropy, as in science, also wins in your application as well. Unless you kind of pay attention to your application's performance won't improve. It will degrade eventually. So therefore, you have to keep in mind and do the performance calculations and performance optimizations as a feature of your development lifecycle. Having said that, I did not come up with all of these ideas by myself. Indeed, these kind of things that I have covered, most of them are a collaborative mindset of a crowd of geeks that are bigger than me. And therefore, I'd strongly suggest to follow them. And this is not a comprehensive list. If you Google around, you can find other people too. And that's it, I guess. And I don't know whether we have time, but I'd love to have your questions as well.